Welcome to the Crazy Hat Chemist. So another video here on electrochemistry. And we're going to be working on some balancing equations here. This is the balancing equation number 2. So I'm feeling kind of unbalanced. Bam! So, balancing equations, electrochemical equations number 2. So, balance the redox equation when aluminum reacts with cupric chloride. So, aluminum. Aluminum is an element, then it's in its standard state, that's a solid, so it's just by itself, Al, solid. And then cupric, what's the charge on the cupric ion? So we've got two different charges for copper, okay, and here is copper, silver, and gold, okay. All of these have one charge in common, and that's a 1 plus, a 1 plus, and a 1 plus. Silver only has a 1 plus, okay. And gold, of course, is worth more than any of these, and therefore it has an additional charge of a 3 plus. That's not why, but it's a good way to remember it. And then copper is less valuable than gold. Therefore, its additional other charge, besides the 1, is a 2. So cuprous is a 1, cupric is a 2, but they all have in common a 1, 1, 1 plus charge. So, hopefully you got the cupric chloride formula. The halide ion of chlorine or chloride is Cl1 minus, and you should get the following on the reactant side. That's aluminum, solid, plus CuCl2 aqueous. Okay, now from this we should figure out what type of reaction this is. What type of reaction is this? We have an element and a cation-anion combination, okay, and that's a compound. So therefore, we should understand that this is a single displacement or a single replacement type of reaction based on that information. Okay, so from this, we need to write what the products are, knowing that this is a single displacement, single replacement type of reaction. So the element, the aluminum in this case, is going to displace a cation or a metal, because aluminum is a metal that forms cations. It will displace either a metal or an element that is in its cation state. In this case, we have both of them simultaneously. That is, the copper is a cation and it is a metal. So the aluminum is going to displace the copper. The copper is going to be on the product side as an element by itself. That's one of the characteristic patterns of a single replacement, single displacement reaction. The aluminum will now combine with the chloride. Now, what is the charge on the aluminum ion? So I've got silver 1 plus, zinc 2 plus, and then what you can't see is the aluminum, that's a 3 plus. So it goes 1, 2, 3, silver, zinc, aluminum. So I know that the aluminum is a 3 plus charge. The chloride is a 1 minus charge. So you should get the following formulas on the product side, and that is copper, that's a solid by itself. Aluminum chloride is AlCl3, aqueous. Now, again, what we want to do, the next thing that we want to do when we have our reactants and we have our products written down correctly, the next thing that we want to do is write oxidation numbers for all the elements in all the compounds. So this is going to be really simple here. Aluminum is an element in its standard state, and that is, it's by itself. It is aluminum, that's a solid, therefore it's a 0. Okay, and then the cupric chloride, how I came up with that formula is the cupric is a 2 plus, that's why there's CuCl2, so it's a 2 plus charge on the copper. The chloride is a halide ion, and that's a 1 minus charge. Okay, on the product side, I have copper that is a solid, and it's an element in its standard state. So since it's an element in its standard state, it's a solid, it's a metal, then therefore the copper has a 0 oxidation number, okay? And I combined the aluminum and the chloride with their periodic trend charges of aluminum being 3 plus. That would be the oxidation number for the aluminum, and the chloride is a 1 minus charge, just like it was on the reactant side. Now what we're going to do is we're going to analyze both the reactant side and the product side and figure out where there are changes. There will be 2 changes, okay, on most examples. And in this example, there are 2 changes. So from the reactant side to the product side, what elements change? The aluminum on the reactant side is a 0. On the product side, the aluminum is a 3+. That is one of the changes, and I'm going to label that as my oxidation because it's going from a 0 to a 3+. That's an increase in oxidation number. An increase in oxidation number is oxidation. Okay? Then, what element changes in oxidation number going from the reactant side to the product side in the opposite direction? And it does have to be in the opposite direction. And that is that the copper is going from a 2+ to a 0. So I'm going to label that going from a 2+ to a 0. That's a reduction in oxidation number. Therefore, that is the reduction half reaction. All right. So now that I've got this labeled, you notice that the chloride ion does not change in oxidation number, so I'm not worried about that. Okay. Now the next thing what we need to do is to divide this up into two half reactions. So I have an oxidation half reaction and I have a reduction half reaction. One of the key things that I'm doing, and I mentioned this on the previous one, is that I'm going to keep that arrow in a line. Okay, that is that those arrows defining the reactant and product side is going to be a vertical line drawn up and down. Okay, that vertical line separates the reactants from the product so I can easily see things. Now the first thing that I need to do is balance for mass. Okay, that is, there's one aluminum on the reactant side, one aluminum on the product side. One copper on the reactant side, one copper on the product side. So this is balanced for mass. I don't have hydrogens, I don't have oxygen, so I do not have to do those sequence of steps in balancing hydrogens or oxygens or hydroxide ions and adding water or anything like that. So now what I have to do is balance for charge. Now remember, you're going to compare the reactant side and the product side. The reactant side for the oxidation half reaction, that's with the aluminum, has a 0 on the reactant side, and on the product side it has a 3+. Now, what's the lower of those two charges? The 0 or the 3+? The 0 is the lower. So that means that I need to have both sides equal the lower of the two charges. So I need to add 3 electrons to the product side. And that's what I've done right here. Now both sides have the same lower charge of a 0. I'm going to do the same thing with the copper reduction half reaction. And I got a copper 2+ on the reactant side and a copper 0 on the product side. What is the lower of the two charges? The lower of the two charges is a 0. Okay, so I need to add electrons. How many electrons do I add? I always add it to the higher number. That is the higher side. And the higher side is a 2+ side. So I'm going to add 2 electrons to the reactant side. Fantastic. Okay, now what I want to do is draw a line here, and I'm going to add up these two equations, the oxidation and reduction half reaction. In order to do that, I need to cancel out the electrons. So I need both sides to have the same number of electrons. Right now, one half reaction has 3 electrons, the other half reaction has 2. So I'm going to multiply both of them by a stoichiometric coefficient. The top one is going to be a 2. The bottom one is going to be a 3. So then I get 6 total electrons that will cancel out. So I'm going to rewrite these after distributing the 2 and the 3 respectively. And you should see that I will have now 6 electrons. And this is the key to all these reactions, is that these oxidation-reduction reactions, when I balance them, I'm going to add up the two half reactions such that the electrons cancel out. And in this case, it's the 6 electrons that cancels out. Now what we're going to do is we're going to apply the stoichiometric coefficients that I currently have right here to the top equation that was the single displacement reaction, and apply those coefficients to what is going with it. That is, aluminum that's a solid has a 2 coefficient. Aluminum that is an ion has a 2 coefficient. The copper that's an ion has a 3 coefficient, and the copper that is an element has a 3 coefficient. I'm going to apply those here to that equation. So now I should do my check. My check is to make sure that I have truly balanced this equation. On the reactant side, I have 2 aluminums. On the product side, I have 2 aluminums. On the reactant side, I have 3 coppers. On the product side, I have 3 coppers. On the reactant side, I have 6 chlorines. On the product side, I have 6 chlorines. I have effectively balanced this equation. Now you can do some additional labeling of oxidation for the aluminum, reduction for the cupric chloride. Hopefully that makes sense for you. That's pretty simple. So we're going stepwise here. Now, additionally, I'm going to mention this, and you could have balanced this equation without using the reduction of the half reactions like I've done here. I could have done this by inspection and just put 3s and 2s in their appropriate places, basically balancing the chlorines, and I would have been done. But I am trying to show you a process, and I cannot emphasize this enough. You have to first learn the process with simple reactions. Once you learn that process, then you will be able to do the more complicated problems, because I am building upon this information to go for the next set of problems. Okay? We can also label this as the oxidation is the reducing agent. That is the species that is doing the reducing. Okay? The reduction is the oxidizing agent as well. Now, I want you to notice that I've labeled only the reactant side. You only label the reactant side. You're never labeling the product side. You're always assuming these reactions and redox reactions go from reactants to products. That's just the assumption that we make here. I am the Crazy Hat Chemist, and I got a great hat here for you. And, I'm a chicken. Okay? So, if you like that video, give me a thumbs up. Please subscribe to my YouTube channel. I greatly appreciate that. Thank you very much. My principal at one time always said, hey, Mr. Montbrion, you have your head up a chicken's... Yep, that's right. Okay, Google me and you can find my website, which my son made, and get yourself a sticker if you donate to my website. I would greatly appreciate that. Or get a cool t-shirt. Okay? I'll see you next time for more cool chemistry videos. Bye for now.